Hello everyone. Let's talk about flux. I want to go over this example and explain some important details I think are confusing for students when we talk about flux. Example, compute the flux of F equals x plus y plus z. I like to start writing it down in a more beautiful form. I like organizing my information. So that is a vector field, right? So it's x comma y comma z. You can keep it with y, j, and k, but I like it this way. Through just the curved surface of this cylinder. So this is vector field, right? Vector field. Say it's an electromagnetic field that is swirling and going with direction described over here. X, y, and z are increasing together, decreasing together, and so on. Now it's going through what? It's going through the surface of the cylinder. X squared plus y squared equals 9. That's a cylinder? Yes, it is. Z is hidden here as 0 times z squared. And because z can be any, this is a cylinder centered at 0, 0, radius 3. So I can sketch a graph for you, like so. And goes infinitely up and down, like this. Let's have a circle, and it goes positive z and negative z forever, and the radius is not 9, 3. And then we're cutting it, we're slicing it with two planes, x plus y plus z equals 2, and then x plus y plus z equals 7. You will think maybe those are planes, that will be like a lead here and a lead here. No, just like x plus y equals 2 gives you a line, x plus y equals 2 is something like this. In 3D, the same thing. It's a tilted plane. So I actually checked it with GeoGebra or any 3D tool you can have, and I'll show you at the end if you want to. And it's cutting like this at level 2 and level 7, like so. So now we have this beautiful shape over here, right? Like this. You can see it like so. And we want to calculate how much flux is going through this shape. And we want to see, is it going in or is it going out? They ask us to find when it's going out of z. So remember, this is my z, right? It's the center of the cylinder and axis of rotation. And they want us to see how much flux is going out. That is a positive orientation for flux. Positive is out, negative is in. I also wanted to say, what does it even mean, this flux is going out? Again, I like to imagine it as a sound or electromagnetic field or anything else. Water, say sound. Sound is going out of this 3D shape, and we want to see how much is actually going through this membrane. Flux measures that. Flux measures some fields going through, in or out. Before we start calculating it, so that's just, I just summarized what we have given, right? This is a given. Physics majors and like to write down given. Then I want to remind you, you should be careful between comparing two integrals. We have surface integral f ds, and we have flux surface integral of a vector field, also f ds. But as you can see, f is smaller and big, and also ds is different. So surface integral of a function and surface integral of a vector field. Here we're talking about flux, so we're talking about vector field here. They're completely different. And here are the formulas. I reviewed formulas for you. Surface integral has this ds tail, I call it tail, which is the size or magnitude of a cross product of partial derivatives of r. So we need to figure out r. R is parameterization, right? R is this u comma v, whatever you name it, du dv. And then dot product here, well, it's a product of a function times a number, because this will be a number, right? Number. because it's absolute value of a cross product. Now the surface integral of a vector field, so flux, has a different formula. The S here is n with a hat. N with a hat is a normal vector. So we find partial derivative of r with respect to u, r with respect to v, ru, rv. Those are tangent lines, right? They are touching the surface, really close to it. When we multiply them with a cross product, that give us sticking out normal vector, and we know that. And it's called n hat because we're working with derivatives, so it's not just n r times z. Yeah, so we need to find derivatives first. That is why it's a different formula. We don't find the size of it. We want to keep a vector. So this will be a dot product, like so. And not the same thing, right? Also, I wanted to say that is why we decide to agree that orientation will be positive when n is sticking out of the surface. That's just agreement. So orientation matters. It will stick out, outwards or upwards. Upwards for graphs, outwards from surfaces like sphere. If they ask you to find in the same example how much flux is going in, say it's the gravitational force is going in, or say it's like electromagnetic field is going inside, what will you do? You just change the sign of n, because we know that. We learned before. To change the direction means change the sign. So how to find out if it's going out or in? Rule of thumb, it's not always working, but a rule of thumb says check the z component. Should be positive. Okay, blah, blah, blah. Let's actually solve the problem, because you need to do your homework and just talking too much. Step 1. I don't see my R. Where is R? Step 1. That is parameterization. You need to learn how to create parameterization. That is the previous chapters we were training you how to parameterize stuff. So with plane, usually x is t, y is z, and y is s, and then you figure out. This one is a known shape. We did it before many times. It's a cylinder. It is given as, let's see, so we want to have cylinder, right? We're gonna have circular, no, it's with I. Circular cylinder. Circular cylinder in parametric form will be x equals r cosine theta or cosine t, you choose. Y equals r sine theta. And what to do with z? Do you remember? Just keep it z. That's what we agreed before for the cylinders. So it's a circle. This is a circle in 2D. That is growing up and down forever and creates a cylinder. Here it is. This is how it looks like, right? So, shape. Then what are my u and v? I'm like, no idea. R is x, y, z. That's how you create parameterization, right? So, we will have r cosine theta, r sin theta, and z. But r is fixed. The thing is, we don't need volume anymore. So it's not like we need to keep r changing from 0 to the number. R is fixed and it is 3. So r is 3. Now I can see not a very good choice of small r and capital R. This is radius. Let's call it capital R, 3. And to be honest, I will just erase this and I will just call it 3. Because it is 3. 3, 3. So our parameterization is now x is 3 cosine theta, y is 3 sine theta, and z is z. This is what you can call, how would you rewrite it with u and v if necessary? Sometimes people do s and t. Note, that does not matter. You just need to be comfortable seeing different notations. It's the same as calling it r equals, so R depends on X, Y, and Z, but X depends on theta and Z. And now because Z depends on Z, sometimes people don't like it. They rename it as U and V, or they rename it as S and T, U and V. But again, that's an extra work, so I don't know why would people do that. But okay, my point is if you see it, you should not be confused. Sometimes S and T, you see it in the books a lot. Usually follow the alphabet S and T, U and V. I would keep it theta and Z, like why even bother, okay? I don't know. Just Z equals Z, what is problem? I guess let's keep it U and V since we just covered U and V. And it matches the nice formula here. Oh yeah, okay, then I can see it's justified. If it is in the formula, then, you know, let's keep U and V then. Good point. So, U is my angle, V is height. We figure out parameterization, put it in the box. That's like super important. Why? Because step 2, we're gonna take derivatives with respect to each variable, right? So, step 2, find partial derivative with respect to U, with respect to V. Let's do that. Partial derivative with respect to U, and then cross product, because why we're doing all of this. Partial derivative with respect to U. I guess let's rewrite it then. 3 cosine U, 3 sine U, and Z is T. V. Z is V. Like this. So let's put that in the box as well. So I need to know where to look. That's why I'm telling you that putting something in the box is important. It's just visually nice to know where to look when I'm working with the problem. So I'm looking at the box. 3 cosine U with respect to U will be... I'm not distracted. I just want to check something. So don't forget, maybe I should put vectors everywhere. That would be more professional, right? Like so. And what the heck is that? That is also not professional. R is a vector. Remember, R is a pointer. R is like a laser that points and describes on the surface. And R has now 2 variables. Used to be just T, R of T. Now R has U and V, but it's a vector that is pointing and describing the surface. So kind of like, let's be careful with that. Vector, vector, vector. Let me make it beautiful. Vector. Now R with respect to U, I'll put it in different color because that will be important. With respect to U is minus 3 sine U, 3 cosine U, 0. Nice. With respect to V is 0, 0, 1. Well, that was easy. Nice. Now we find cross product. So maybe, why even like bother writing it down separately? If now we have to rewrite it again. Step 3. If you're good with steps already, then skip the step 2 and put it right away in the determinant. 3 R with respect to U times cross product R with respect to V. That gives you N. That gives you N hat, the normal vector. Bar I, J, K. And now you see I have to copy it again, so kind of like, don't write down I, J, K first, it will not fit. Minus 3 sine U, now J. 3 cosine U, now K. 0, 0, 0, 1. Nice. Quickly calculating it. I is multiplied, or you can write down if you want, at least once. Let me use I, J, K. I, J, K, those are vectors too. I is multiplied by 3 cosine U minus 0 minus J, which is multiplied by minus 3 sine U minus 0, and then K plus K is multiplied by 0. So K is not there. So normal vector becomes 3 cosine U, comma, plus, minus K, plus 3 sine U, comma, 0. And this is the big difference, is with the next step. If this is surface integral with small f, a function. Then we find the size, the magnitude of this vector. But if it's capital F, which is a vector field, flux, then we don't. We keep it as a vector and just multiply it by F. So this is how to remember. If you see flux, that's not even a question what to do. Flux means we don't find magnitude. If you see some problems with mass and fluid density with C or F, density, then it is small f. And then you find their size. So the next step will be depending on the problem. Since it is flux, maybe let me write down. Step 4. Flux means no need for the magnitude of this product, cross product U and V. So maybe just remember. So we're going to step 5, and the last step is the same. We need to convert the F we are given. F is X, Y, Z. That's the flux. In this case, it's flux. In the other case, it's a function. It's written in terms of X, Y, Z. Your job is to convert it, rewrite it in terms of R, right? And R depends on U and V, in this case, because it's a surface. Sometimes it's just T. U and V are not factors. I put too many bars. That's a bit too much. Okay, so let's do that. F will be, this one is easy. We just need to plug X, Y, Z. So X is 3 cosine U. Y is 3 sine U, and Z is V. Wow, that was like lots of work. No, it was not. So I basically just copy paste this amazing. See, that box was very important. In this case, I copy paste, but if everything is squared or square root multiplication, then it will be harder. Finally, the last step is also the same for both. It's a product. Step 6. Finally, we're writing down the integral, or you can actually find the product first if you want. The product will be capital F times, they call dA. And in this case, whatever you found in the step 3 and 5, right? So let's put them in the boxes. I will multiply my n, which is normal vector, by f. And it's going to be a dot product, not the cross product. So n with a hat, normal vector, and f, that is vector field. Vector field. So they say that we want to find the flux of that vector field. So how much is going out? Oh, before we do that, so let me, I guess, rewrite the idea. We're going to multiply these two vectors. F is 3 cosine U, 3 sine U, and V. I would not even rewrite it. I would just multiply right away because too much writing. And the other one is 3 cosine U, 3 sine U, and 0. 0, that's nice. I like zeros. So before that, you know what I need to check? If I need to check if n should reverse the sign or not. Should we use n or minus n? So how to do that? Well, we need to figure out that the vector cross product, this vector, is going out of the cylinder, not in. I told you that we should check if z is positive. That's like rule of thumb. In this case, it's 0, so like, okay. But it says positive or 0, so it's fine. The point is it shouldn't be negative. If it's negative, usually it's stuff going in. But we also can check just based on this. 3 cosine and 3 sine. And then 0. Are they going in or are they going out? When u is increasing. U is the angle. Well, they're going x, y, and z. So x, y, and z, here, right? XY. So we want to see if Z is increasing with time, or at least not decreasing, I guess. So I can say that the cross product points away from the Z-axis. Then we keep the same sign. We don't have to change the sign. There was like a beautiful picture over here. I wanted to show you this. It should look like, if they ask about the positive one, it should look like this. It should go out, not in. But if they ask for it to calculate the flux that goes in, so actually we can find more, any. But this is called positive direction, positive. So if they ask how much stuff is going in due to the gravity, then you just use minus again. So that's not very hard. Again, maybe sketch the graph of that vector field, of that cross product. What does the cross product do? But in general, you see, we just keep checking if it's positive or zero. And if it's negative, we're changing the sign. That is the idea. There was example in the homework when it was negative. Okay, let's finish calculation. This one is pretty simple. It's a dot product. Let me write down. Dot product. Dot product means I'm multiplying components and add the results together. So don't mess up this simple step. I know there are too many things to remember, but just be careful. 3 cosine square u, no, it's 9 squared. 9 sine square u and 0. And we're adding together. Remember, dot product gives you a number. In this case, it's a function, but not a vector. And then I would say that you need to integrate. So last step is step 7. Step 7 says find the integral of this flux. Flux. Integral over S. F dA. Let's compare the formula we have in the table. In the box, it looks like this. Flux, surface integral of F gives you flux. So we calculate everything. You see, sometimes they call DS, sometimes they call dA. That depends on the book, so don't be confused with that. And we have it here. We definitely know what's inside. Inside is this function in the purple box, which, by the way, simplifies to just being 9. Duh, that's just 9. By the way, if you use the notation of FDA, then at the end of this dot product, so let's not be confused over here. Let's be careful with notation. F times n hat gives you 9. But if you want to know what is FDA, FDA will be, skip some step, it's going to be 9, and then dA is n, and then du dv at the end. So it's going to have du dv. Okay, du dv, that's double integral. And the cool stuff is that we know what's inside. Inside is just 9 du dv. That's pretty cool. So the last step is to figure out what is happening with u and v. Not very obvious, to be honest. So one is obvious. You choose. I would say the angle one. The angle is u. So let's put. Actually, we don't have to change the notation, du dv. So let's put the angle. It's from 0 to 2 pi, not surprising because we have the whole rotation into d, right? V, so this is theta, remember? So theta, we chosen to be u, and then z was chosen to be v. That's height. That makes sense. So now we just need to find how high the z is going. Z is going from 2 to 7. Yeah, not really. Z is not going from just height to height. It's going from plane to plane. So we need to figure out that. It's not very hard. Don't be too scared about that. Solve for Z here and solve for Z here. That's what it's going. And remember that your Z is your V. And that's why I'm not a big fan of renaming things. Because, like, why would you now have to figure out the notations? If you know how to code, you know that this is annoying to rename the variables. Why would you do that? Anyway, we already did it, so let's keep it. So let's figure out u is between 0 and 2 pi. I think you can all agree on that. We have the full rotation. But v is between what? Well, I will solve for z from the first equation. We had x plus y plus z equals to x plus y plus z equals to 7, right? Yes, 2 and 7. So solve for z. Z, the smallest z that we can have is 2 minus x minus y. And the largest z that we can have is 7 minus x minus y. So guess what? That's what's going to the limits of integration. The problem is that we're talking about z or v, blah, blah, blah. Too complicated, but we need to rewrite it in terms of not x and y. So pay attention. The small one, the smaller one, is 2 minus x. X was 3 cosine t. Okay, it's not gonna fit. 3 cosine t and minus 3 sine t. Finish it without me, because my computer is slowing down. Minus 3 cosine t minus 3 sine t. That is the smallest v we can have. And then the biggest v, you can guess, will be 7 minus 3 cosine. It's not t. T is my u. I just looked at the book and then that one has t. It got me confused. U minus 3. Remember, it's not sine, not 9 also. That's kind of important. And that's what you're going to put here, which will be hard to write, but okay. Challenge accepted. 2 minus 3 cosine u minus 3 sine u. Sine u. And then this one will be, I will step away, 7 minus 3 cosine u minus 3 sine u. Nice. And now you can integrate. So we should have changed the order. Now I can obviously see that. If you leave the integral like this, the answer will be a function, but we need a number. Flux is a number. Bigger or smaller tells you how much flux is going in and out. It's like a membrane, and then how much blood is going through the membrane in your vessels and so on. So it should be a number. It should not be a function. But if I integrate this first, that will give me a number, and then this guy gives me a function. Order matters if one of limits of integration or more are functions. Number should be always the last integral. So 0 to 2 pi should be the last integral. That's why, let's fix it. Luckily, it's not very hard to fix. Check it out. Check this magic of fixing the mistake. We have d v first and then du at the end. So I'm just erasing this nice integral over here. Moving everything to the left. 9 dv du. Okay, v is already written, and I'm just gonna sneak right before u. The integral from 0 to 2 pi. Genius. I'm very proud of myself. So from 0 to 2 pi, that's a definite integral. We know that the answer for that is going to be 2 pi. And now we just need to integrate 9 dv. So 9 dv is just v. And I'm plugging top minus the bottom. And it's going to be 7 minus 3. How many times I wrote down this thing? Minus. So did you finish without me? That would be nice. Minus. Let's change the signs. 2 plus 3 cosine u. You could put parentheses, but I'm just good at changing all the signs. Close, close, cancel out, magic. Minus 3 cosine. Can you like change the color, please? Minus 3 cosine u plus 3 cosine u minus 3 sine plus 3 sine. 7 minus 2 is 5. 7 minus 2 is 5. And the answer does not match what I missed 9. That's why, like, wait, why do they have 45 and I don't have 45? There's 9 in front of everything. Okay, that's very good. Like, do not mess up too much. So let me put like fat red equal sign, and continue over here and put all of this in the box. That's like explanation of limits of integration, right? I like doing that. My students' notes usually have that kind of notation a lot. So the answer will be 9 times 2 pi times 7 minus 2, which is 5. That is still not 45. But 7 minus 2. 7 minus 2 is 5. So what is my problem? Oh, it should be 90. It's not supposed to be 45. It should be 90. See, I need to be more confident. Pi, don't forget the beautiful pi. Pi you can even approximate as 3.14 and so on. So you know how to do that. 3 times 9 is 45.1459 and so on. So you can, well, probably it's 41 over here because it's 90. So you can even figure out what does this number look like. That is my explanation. I'm not sure if the video is too long or not, but I mean, you can stop if you want. I just wanted to show you how you can actually visualize all of this if you want to. Pretty cool. You can use different tools. This time I decided to check GeoGebra, which I usually don't use, but it's super fun. I don't know why I'm not using it. So I want to plot the cylinder, x squared plus y squared. Look how cool it is, right? And it's paraboloid. And then the moment n equals 9 becomes a cylinder. And then I'm cutting it through with two planes, x plus y plus z equals to 9. And I will copy that. And then no, it's not was 9, it was 7. 2 and 7. Okay, I don't see the planes, but then I'm removing it. Look how cool is that? So that's whatever is happening. So we're not talking about volume, remember, not anymore. We used to talk about volume too a lot, so now we don't do it anymore. And then there's a flux going from this blue line, which is the center axis of rotation, right? Z. And the flux is going out. They want to see how much it will go through that surface. So imagine that these planes and the red part of it, like membrane, and you're engineering and you're building and figure out how much blood will go through this device. If you put this device in the vessel, for example, you need to slow down or clean the blood. So how much will go out? And if you want to see how much will go in, do you know what you should do? Actually, let me make like a cool screenshot and put it in the notes. Like that. Do you know what you should do if we want to know how much is going in? Correct. You just change the sign of n. That n we calculated. The n we calculated over here. If they say, okay, so you already found how much is going out, 90 pi, can you find how much is going in? Well, then you're like, no problem, I'm just gonna change the sign. That's it. And then how to change the sign of the vector, I'll use minus 3 cosine and minus 3 sine and blah, blah, blah. And the answer will be a number, but it's just gonna be a different number. Make sense? So at the very end, when this dot product is happening, this will be negative minus 9 cosine squared and minus 9 sine squared. And this will end up to be minus 9 here. And the answer will be minus 9 plus 2 pi plus 5. And the answer will be minus 90 pi. So as you can see, all of this has very intuitively correct intuition going in and going out. The negative number shows you that things are going in. No, you do not want to copy it. Oh, let's see if I can do it. Nice. Look at this, how beautiful it is. Okay, I hope you enjoyed the video. Keep working hard. Flux is the very last topic of the semester, so it's hard to enjoy it because you're tired. But not only it goes to the exam, most of the time free response question and a short multiple choice question too. But also it's just pretty cool, you know. Flux is a cool idea of things going through. This is the example of gravitational forces, electromagnetic forces. How about water going through some porous surfaces? How about the sound going through the membrane of your ear? Like, all of this is really, really fascinating. Anyway, thank you for watching and keep working hard, and I will see you next time.